You are once again welcome to Population Genetics and Evolution, Unit 5, Session 6, the role of Darwinian evolution in complexity growth. And by the end of this session, students should be able to discuss the effects of Darwinian evolution on complexity and the relationship between evolution and complexity. Let us consider an abstract generative system of which we only know two things. One, a certain design generator is being used to generate new designs. The particulars of the design generator define a certain space of possible designs which can be explored. The next is new designs are being generated according to a certain heuristic. In other words, the space of available designs is being sampled in a certain sequence as specified by the heuristic. So for now, we assume that the heuristic used to generate new designs is unknown. It could be random, evolutionary, hill climbing, or anything else. We now ask the question, what is necessary for such a system to produce unbounded growth in functional complexity? A moment's thought suggests that in principle, at least two conditions are absolutely necessary. First, the system generator must in principle be able to generate arbitrarily complex designs. Second, the search heuristic must not impose a hard upper bound on adaptivity or functional complexity of the designs being sampled. It need not favor complexity. It may even discriminate against it, but not to the point of forbidding it entirely above a certain level. Inefficiency, however, another moment's thought will make it clear that without any furtherance device, such a system might well take possibly long times to come up with any such complexity. This because functionally complex designs are rare in the space of all possible designs. A random design generator may come up with arbitrarily complex designs given enough time, but what good would that be if enough time exceeds the thermodynamic limit of universal heat death? Another difficulty occurs when designs are eventually removed from the system. For example, designs might have a specified maximum lifetime, which would mean that all designs are eventually eliminated, or the population could have a maximum size, which implies that some designs must be eliminated. In this case, while the system will still come up with designs of unbounded functional complexity over time, we have no assurance that the maximum of complexity at any time will sustainably increase. This is because without any further assumption, we have no way to know that the rate at which complex designs are being generated balances the rate at which they will not be removed. In fact, the opposite is much more likely. While arbitrarily complex designs will eventually occur, these designs may very well be mere blips in an otherwise consistently low background. If the current maximum of complexity is removed, we have no assurance that it will be replaced by designs of similar complexity. The Darwinian heuristic. Now let us introduce a new requirement. We posit that our system is evolutionary, that is, it follows the Darwinian heuristic as elegantly formulated by Wagner and Altenberg. The Darwinian heuristic is to choose sample points by perturbing the more fit ones among those sampled thus far. In other words, new designs are not generated arbitrarily. Rather, existing designs are evaluated after a certain metric, their fitness, and those designs which exhibit a relatively high fitness are selected as starting points for small jumps towards newer designs. Our question is, how does this new specification affect the emergence of functional complexity? The Darwinian mechanism restricts exploration. The first thing to note is that the Darwinian heuristic actually imposes a restriction on the search process. The search process will now follow certain directions at the expense of others. This restriction constrains both the scope and the direction of the search process. The restriction in scope comes from the fact that because evolution proceeds by small jumps from existing designs, Newer designs can only be chosen in the neighborhood of the current population. The restriction in direction comes from the fact that only those designs which exhibit a high fitness will be used as starting points for further exploration. In unfavorable conditions, this restriction may severely limit the exploration of design space. For example, if the population happens to be in a certain domain of the search space which is entirely surrounded by relatively unsuccessful designs, then the process may well end up being trapped into that domain. Conversely, potentially highly fit designs may never be reached if they are surrounded by a region of unfit designs. This suggests that at least two conditions for complexity to appear in evolutionary systems, namely that it should be successful and reachable. Benefits of the restriction. On the other hand, this restriction has important potential benefits. First of all, when successful designs are found, they will tend to be preserved even beyond the lifetime of individuals, or at the very least, they will stand an immensely higher chance of being preserved than under random edge, as long as they remain successful within the context of the current population. This permits the persistence of functional complexity, despite its rarity in design space, even in the face of finite lifetimes. Complexity is no longer condemned to occur only in short blips over an otherwise simple background. Furthermore, as we have already noted, adaptive functional complexity tends to come in loose clusters in design space. If we want to obtain a successful complex design, we stand a much higher chance to obtain it by slightly altering another successful design of lower complexity rather than by randomly poking at the entire design space. The consequence is that by preserving existing complexity, that successful complexity, the Darwinian heuristic also facilitates further increases in complexity, provided such increases are possible within the neighborhood of the population. A successful complex design may act as a stepping stone towards even higher complexity. This is, in essence, the basis of the blind watchmaker mechanism, so vividly expounded by Dawkins. By slowly accumulating small beneficial improvements, each working as a stepping stone towards the other, the Darwinian heuristic may eventually produce enormous amounts of adaptive functional complexity with incomparably higher probability than under random search. Thus, we see that certain requirements must hold if evolution is to generate designs of unbounded complexity. It is necessary that at all times successful designs of higher complexity exist within the current neighborhood of the population. At first sight, these conditions might seem rather straightforward. However, are they really sufficient? In review, the limitations of non-evolutionary complexity growth include finite populations and finite lifetimes. Darwinian heuristic actually imposes a restriction on the search process. The restriction constrains both the scope and the direction of the search process. The restriction in scope comes from the fact that because evolution proceeds by small jumps from existing designs, newer designs can only be chosen in the neighborhood of the current population. The restriction in direction comes from the fact that only those designs which exhibit a high fitness will be used as starting points for further exploration. Restriction has important potential benefits. First of all, when successful designs are found, they will tend to be preserved even beyond the lifetime of the individuals. This permits the existence of functional complexity despite its rarity in design space, even in the face of finite lifetimes.